what I'd like to do is give you an introduction to kind of what water is, what the water problems are, and then what aquifers are, and how these aquifers are controlled by the structures around us, and what the structures regionally are in West Texas. And then I'll give you an introduction to the aquifers in this county, and that way you might have a chance of understanding James Beachy's terminology when he comes around. Now, one thing about geology is we're full of terms, and so please, if anybody, if I run over something that doesn't make any sense, just stop me and we can address it. So one of the main issues that in my career that I've faced is everybody's interested in water, but it's the fundamentals of life. And so without it, nothing occurs at all. And its molecular structure is odd. It does a lot of strange things. It's incompressible. It's known as the universal solvent. When rainwater falls from the sky, it has a pH of 5.4, and it is completely inert. So if I was hanging out just in a bathtub full of rainwater, and you wanted to get rid of me throwing a toaster in with me, and nothing would happen. You just toss the toaster in with me, I get out and get upset with you with the toaster. But if you get in a deal of Madera Valley water and somebody tosses a toaster in with us, it has a lot of dissolved constituents within it, and it conducts electricity, and you would get the job done. Every one of these waters kind of begins in a unique way, and it's going to go through a cycle. But most of Earth's surface is covered in water, but there's a very small amount. This is what I always think is fascinating, is there's a very small amount that's actually usable for potable water, for humans or cattle or anything else. It's very, very minuscule. And potable water is typically thought of as unpolluted water that's suitable for drinking. So you don't want to go to Denver City and drink the water. We were up there one time, and a bunch of hillbillies from Kentucky were with me. And it said non-potable water, do not drink the water, but they didn't read that, and their lips swelled up overnight. It was kind of fascinating. So you gotta read. You gotta read. When we start looking at that 3%, it's broke down even a little further. Of that 3%, 78% of it's locked up in the ice caps and glaciers. 20% is kind of groundwater, and then we wind up with soil content, water. It's just interesting to think about. Each time we talk about groundwater, we're getting smaller and smaller and smaller in the percentage of water that's actually usable. And this is where it gets to be quite interesting, is how long does it take water to go through a system? And we can date these aquifers in West Texas using different kinds of isotopes. There are several of you guys in the room that are far beyond any of our abilities in understanding dating water. How do you determine where water comes from? Essentially, what we're going to study a little bit here in a minute is the fingerprint. Hey, water's going to have a fingerprint of the type of system it's been in. And so if it falls from the sky inert, and then it begins to kind of take on chemistry associated with a rock, we can back calculate things like how long it's been in the ground, how long it stayed there, how quickly from the time it rains out until it runs off and gets into the ground, how it goes. So this is called the water cycle. And I know that's kind of an elementary diagram, but simple's more sometimes, right? This here controls everything. Now, as that water begins to get into the subsurface, we start getting into geologic and hydrogeologic terms. The term aquifer itself is a zone of saturated sediment, pretty much somewhere in the subsurface that you're gonna hit. And then in some places in the subsurface, there's confining layers, which are gonna, oh boy, I did it then, which are layers which allow water to actually quit moving downwards. They're gonna be things like clays, in lots of cases, things that are considered impermeable for water to move through. And as water percolates down in a system, it will start to migrate lateral. And whenever this happens, we start getting into the idea of an unconfined aquifer is essentially a shallow system that sits on top of one of these confining layers. And then we get into confined systems, which are essentially aquifers that are stuck between two of these confining layers. They're typically deeper. And we see all kinds of geologic wrecks occur depending on what kind of aquifer we're in and how much production's occurring in a region. There's lots of cool things can happen, like sinkholes can develop and hazards, geologic hazards associated with these. So in cross-section view, your confining layer can be like a clay, something of that nature stuck around here. That makes the water actually mobilize lateral, and then it'll push back up, and it can actually feed streams. It can become artesian for springs. That kind of thing occurs. We can also see water get into between these confining layers, and it can become long-distance travelers at this point. They can go hundreds of miles between these layers and take on all kinds of fascinating chemistries and show up in really neat locations. Now, depending on the rock type that we see associated with this kind of stuff, we start seeing waters move either quickly or slowly. And so the speed at which they go through this whole system is a residence time. So when we start talking about these water tables, some of the terms you're going to see before long are like the term head. It's where the water table actually is in a system. Where do you hit that saturated zone in the subsurface? And then you got to have a little bit of a diagram just to make you remember physics, right? And calculus nightmares that you had. There's a point in a well where you actually drill the well, and there's a point where the water can infiltrate in, and the water comes up a well. Here's your water table. So you got your depth of water and your pressure gradients. This is above a gradient typically set to sea level. And so when we start looking at water table maps and creating these water table maps, they're all set to datums, and they're typically going to be set to the average sea level. So we'll be looking at meters above that. And so some of the maps you'll see in people's presentations later, this is what they're speaking of, and this is how you calculate where the top of that water table is. And it allows you to figure out lots of cool things, like where the water is actually moving and the driving forces of the movement. Now, you can't do any of this without one fundamental set of mathematics. And I always think this is fascinating, because when we start trying to calculate water movement through the ground, it's an art form. It is no longer science, in my opinion, because you start hitting a gravel, for instance, is not uniform. So in some zones it's fine, in some zones it's coarse-grained, so water starts to migrate differently according to how it's mobilizing out. We owe every bit of being able to figure out fluid dynamics to this particular equation, which looks quite simple. And there was a gentleman by the name of Darcy who was a sewer engineer. Literally, he was trying to figure out how much crap can go in a pipe and successfully drain a system. And that became the entire future of everything we do in groundwater and fluid mechanics comes out of this. And so essentially, you start looking at how water can move through a system based off of how big the grains are and how tight the grains are. And then you have rise over run, change in elevation over distance, and we can determine how water's moving through systems, how quickly it's going in a different direction. And we owe it all to Darcy. So when we get into a cross-section of these and how this water moves, that art form of mathematics and physics can be applied, and geology. So we're combining a lot of fields here. We're going to combine fields associated with biology, because a lot of times little organisms can create little microhabitats in the subsurface to prevent fluid flow. But we're going to combine things like chemistry. We're going to combine the physics of it. We're going to combine the geology of it. We're going to combine those into a field of geomechanics and engineering geology. And then we start figuring out the fluid through all of this. So when we see a simple map, like I'll show you in a little bit, it wasn't that simple to create, even though it's something that flies up and we can see it in like 2 seconds. Now in West Texas, here's the fun part. So that's the water part. Introduction to what a system is, how a system moves, what a system can be problematic doing. West Texas is fascinating because it holds 3.6 billion years of Earth's history, all right in this little area. And there's several of you have been in the field with me that are in this room for weeks and months on end. And we go out and we would get confused and stare at rocks till you thought you saw something cool. Mainly just the heat getting to us. But what you see here is the Appalachian Mountains in the subsurface. And what is really fascinating about the Appalachian Mountains in the subsurface is they're following a preset set of mountains that are known as the Grenville. Now, the Grenville Mountains are the oldest mountains in North America, 1.6 billion year old orogeny, which is a mountain building event. They were right here, and they show up, and they're exposed in the Llano Uplift, and they're exposed out here in Van Horn, Texas, at the surface. And so that represents the coming together of something quite phenomenal. 1.6 billion years ago, this area sutured and became something referred to as Gondwana land, which is the first supercontinent ever produced on North America in the globe, but North America was right in the heart of it. It begins to break apart after that. It breaks apart into things that you hear about, like Gondwana land and Pangea, and cool things of that, microcontinents. Then it comes back together, into our Pangea system. Now, Pangea is represented. This is the suturing about 250 million years ago of the bottom of the Appalachian Mountains. They began at Newfoundland on the northeast coast, and they come all the way under Alabama, up into Georgia. They're exposed in Oklahoma, and then they pop out right here in little old Marathon, Texas. And so from my backyard in Balmorhea, when you're looking at the mountains, this set of mountains here, you can see them. That's the Appalachians exposed at the surface. On this side, we come in here later, and we're hit again. This is called the North American Laramide Cordilleran, or the Laramide Cordilleran. Some people call it the Rocky Mountain orogeny. It begins about 66 million years ago for us out here in West Texas, and we see compression structures from this direction. This is responsible for the Davis Mountains, the Barilla Mountains, all the volcanics we see in West Texas show up here. Then something quite fascinating occurs. When Earth gets hit like this, it begins to expand. And so what you start to see is an expansive system known as basin range. It starts in our backyard in Reeves County. The first fault you see arguably could be in Pecos County associated with extension. But these are big normal faults where you start seeing offset. It happens from here all the way to Bishop, California, where Mule Days happens to be for any of you other mule lovers. I may be the only one. But that's where we go with our mules to have a good time. They got the largest mule rodeo in the world, and they got the westernmost exposed fault associated with basin range. So I go see the one at my house, and then I go see the one on the west coast. That continues today into modern Rio Grande Rift. North America is splitting in half at about 2 centimeters every 10 years. We've discovered the Rio Grande Rift right in this area here, and up here in New Mexico. North America is actually breaking in half. And so George Strait will be right. You'll see oceanfront property right here somewhere in Arizona, but we'll have it more or less right here in Van Horn, Texas. So I bring all this up. So we've been hit and extended and hit and extended and hit and extended multiple times in West Texas. Every one of these structures has a defined orientation and characteristic about it. So you go out in the field, you do a bunch of mapping, and you can determine whether you're looking at these marathon structures, or whether you're looking at laramide structures, or whether you're looking at basin range structures. These have a northeast trend to them. These are northwest, and then you have a north-south. Now, all of this has to be understood before we can decide whether or not we can move a fluid through it, is we have to know what the rocks are doing. And it doesn't matter what the fluid is. It could be oil and gas, or it could actually be, water. I love this map, mainly because it's just colored. But we start seeing the geologic provinces of Texas. Texas is quite complicated. And in West Texas, it's even more complicated. Everything out here to the west is the volcanics. Then we have the Edwards Plateau, we have the Permian. It's just an absolutely phenomenal place. In Earth's history, Earth has been underwater where we're standing 6 different times since the early Cambrian. Life on Earth begins right here at 540 million years ago. There's been 6 major transgressive events where ocean levels flooded Central North America completely. We're underneath one of these times here where we're actually exposed, but sea levels have gone up, come down, and each time there's something catastrophic here where you see all the organisms in Earth's history pretty much evaporate. Like at the end of Permian, 95% of stuff disappears off of Earth's face. At the end of the Cretaceous, another major mass extinction event. This represents the end of the dinosaurs and the beginning of, mammals kind of beginning to get a stronghold. So the structures that you see in West Texas are phenomenal, and in Reeves County has all of them. And it is absolutely phenomenal. And when we start looking at aquifers in Reeves County, we have to look at dissolved constituents within these aquifers. The dissolved constituents, a lot of people will call total dissolved solids. Things considered like drinking water standards are typically less than 1,000 of everything total dissolved solids. You start getting in the brackish waters at 1,000 to 10,000 parts per million. And I'll show you what these mean in a little bit. Then you get into saline waters and brine waters. And as you'll see in other folks' talks here before too long, we're going to actually see the gamut of these in West Texas, in Reeves County, before the day's over. You will have talks on brine waters, you'll have talks on brackish waters, and then you'll see those of us that are lucky enough to have drinking water, and our water systems are all having to meet these standards, which thank goodness for all of the water systems. I see some of the representatives in here. Thank you for providing us drinking water, because it's not an easy task. River water, though, when we start looking at this and how it gets in, typical river waters on the East Coast and things have a total dissolved solids of less than 230. As you get into Western North America, though, they start climbing predominantly because of evaporation rates. We have larger residence times of water before it gets into the aquifers, and then we actually don't have water flushing through systems like the Colorado River. If y'all been watching it, it's not even making it to the Mexican border now, just completely dry. These major ions provide something referred to as the major eights. These are all the dissolved constituents that give a water its chemistry and give it its fingerprint, which we back calculate to its rock type. The most prevalent in West Texas are bicarbonates, coming directly from limestones and dolomites, that kind of thing. And then we have minor solutes that we start getting into. But if you take a water sample in and you ask for an analysis, these are going to be your dominant ones: calcium, sodium, magnesium, and then we get into these complexes, bicarbonate, sulfate, and chloride. The driving factors of chemistry and what allow these chemistries to have their factors are evaporation, which we have plenty of in West Texas. Weathering, remember this chemistry of this water, it's acidic when it hits a rock, and then it begins to equilibrate with the rock chemistry. And so it's going to take on these minerals by dissolving it out. This is how caves get started. We start seeing water moving through a limestone, through a fracture. It'll eat out a tiny little zone, and it'll eat out a larger one, and next thing you know, you have a cavern like Mammoth Cave in Kentucky, or San Solomon Springs. It's thought here in Reeves County that it's driven by caverns in the subsurface where water's moving through it. Ion exchange, we start having different minerals come in contact with different kinds of water, and you'll see this. This acts almost like your water softener at your house. So for you guys that have a water softener and you put salt in it and the sodium, it exchanges out with these guys, and then you get a soft water, but then you have high blood pressure, right? Yeah, so you always have some sort of offset. And then we wind up in nutrient problems. My PhD was completely done in 7 different disciplines: in engineering, soil chemistry, soil microbiology, soil physics, hydrogeology. And one of the most fascinating things about it was we were studying contaminants of all kinds. And then we start adding these into this, and we really get to have fun. Our aquifers in West Texas, specifically under us, are broken into major stratigraphy. And so when we start talking Ogallala aquifers, well, these are tertiary age aquifers, meaning they're about, anywhere from 66 to right at maybe, something on the order of 15 to 20 million years old. We get into Cretaceous systems. All right, we start seeing things like the Edwards aquifer here. At the base of it's the antler sands. And so all of these different little aquifers are water producing, and they hold specific water chemistries that you can tell apart from each other. We get down here into the Dockham. This is a major aquifer here in Reeves County. So we don't really see Oglala here, but we see younger rocks in Reeves County. So the chemistries of these fingerprints we put on these sweet little Piper plots, and they land in zones. Each type of aquifer will give us a different fingerprint of where it goes, and then you actually have the amount of ions in it. You can make these plots, and then you wind up being able to predict what aquifer you're dealing with, which rock it came out of. So as an introduction, I've spent the better part of 20 years doing research in Reeves County, Jeff Davis County, Culberson County. And now we're working on Pecos County, but here's our area. We've done a lot of research in this part of it. But we actually have 2 aquifer systems that are deemed by the Texas Water Development Board under our feet as major systems. First one we're going to see is the Pecos Valley alluvium system, and then we have the Cretaceous Edwards Trinity. This is a major aquifer. It goes all over Texas. It changes names. It's so cool. Rocks change names about 4 different times. The same rock as you go from here to East Texas. So terminology becomes problematic. Now the minor aquifers in Reeves County are a little easier to come up with. Here's the Dockham. And then we have the Rustler, which is part of the Ochoan series. And then you actually have something that everybody forgets about called the Capitan Reef Complex. Now the Capitan Reef Complex is exposed in some places, but it's thought to actually be responsible for lots of the water we see coming to our springs in the southern part of this county. The reason we have to cover this whole area is like we'll see in future talks, a lot of our springs are on county lines. It turns out water doesn't care which county it's going through. And so we start having problems when we have boundaries, and water does find its way this way and that way and this way. So then now we have other issues and it becomes more of a legal battle. I absolutely love this particular thing. I realize it looks like something terrible happened to this map. This is the best map I've ever seen to demonstrate the complexity of the geology in West Texas. And so you can see it again. You're going to have all kinds of great stuff here associated with the Appalachians. You got all the sweet uplift over here and the Diablo uplifts. And I just glanced over these basins. You know, we can go over these Permian Basin things for weeks, and it's just ultra complicated.